Hello and welcome to my channel Maths Hub by Dr. Tanya Bose. So today in this video I'll talk about applications of partial differential equations and I will be modeling one-dimensional heat equation in this lecture. So previously in my previous video you have seen how to solve a one-dimensional heat equation. So today I will be focusing on how to model it, right? Okay. So in one-dimensional heat equation, what was the model? The modeling says that we consider a uniform rod which is homogeneous of length L and it is placed along the x-axis with one end at x equal to 0 and the other end at x equal to L, right? So you can see that this end is kept at x equal to 0 and the other end is kept at x equal to L. We assume that this rod has a uniform constant density rho and it has a uniform cross-sectional area A. So we also assume that the lateral surface of the rod is impenetrable to heat transfer. That is, it is insulated laterally, so no heat flows along the lateral side. So heat only flows in the x direction, right? So these are the assumptions that we make before we model this heat equation. So now, for heat conduction, what all we need to know. So first thing that we need to know is that heat always flows from higher temperature to lower temperature, right? Secondly, the quantity of heat in a body is always proportional to its mass and temperature. And third, the rate of heat flow across an area is always proportional to the area and to the rate of change of temperature with respect to its distance normal to the area. So using these three rules, we will frame the one-dimensional heat equation, right? So we try to model this one-dimensional heat equation. So we assume that let ux comma t be the temperature of the cross section at the point x at any time t. So we denote u with the temperature. Now, if delta u be the temperature change in a slab of thickness delta x of the bar, then the quantity of heat in this slab. Now, how do we calculate this quantity of heat? We did one of the rules in the previous slide that the quantity of heat in a body is proportional to its mass and temperature. So we assume that let the quantity of heat be Q. So what is Q proportional to? It is proportional to the mass and the temperature. So the temperature here is delta U, right? Now we know that what is density equal to? Density is always equal to mass by volume. So what will be mass equal to? It will be density into the volume. So what is volume here? A is the cross-sectional area and the thickness is delta x. So let us place this value. So we get Q proportional to rho A delta x and delta, right? Now when we remove this proportionality symbol, we get Q is equal to S times rho A delta x and delta, right? So here, what is this S? This S is the specific heat, right? So this is how we calculate the quantity of heat in this slab. So I hope till here it is clear. Now we move on to the next slide and see how to develop it. Now, we assume that in this slab, at this point, this is x and this is the change delta x. So this point is x plus delta x. So here, R1 is the inflow of heat, the rate of inflow of heat, and R2 is the rate of outflow of heat. So we calculate what is the rate of increase in this heat, right? So what is the rate of increase in this heat slab? So we calculated the quantity of heat. So the rate of increase of heat will be now S rho A delta X delta U by delta T. This will be equal to what will be the rate of increase now? it will be R1 minus R2, right? So R1 is the rate of inflow of heat and R2 is the rate of outflow of heat. Now, how do we calculate these R1 and R2? So, we did the third result in heat conduction, that the rate of heat flow across an area is always proportional to the area and to the rate of change of temperature with respect to its distance normal to the area. So that means what should be R1 equal to? R1 should be proportional to the area into the rate of change of temperature, that is del U by del X at the point X, right? So from here, when we remove this proportionality symbol, we get R1 is equal to minus K times A del U by del X, the rate of change of the temperature at this point, at the point X, right? So we get R1 as minus Ka del U by del X at the point, right? Similarly, what is R2 rate? R2 is the rate of outflow of heat. So according to the same law, we can say that R2 is also proportional to A times del U by del X. But now what is the point? The point is at X plus delta, right? So when we remove this proportionality symbol, we get R2 is equal to minus Ka del U by del X at the point X plus del X, right? So here what is K? K is called the thermal conductivity, right? So now let us place the values of R1 and R2 in this equation. So from here, what do we get? We get S rho A delta X delta U by delta T is equal to minus R1 was minus Ka del U by del X at the point X minus, so the second time the sign will change. You will get del U by del X at the point X plus delta X, right? Now after equating, you can see that the cross-sectional area A gets cancelled from both sides, right? So from here, what is del U by del T? Del U by del T comes out to be K is constant, S and rho comes out, and we get del U by del X at X plus delta X minus del U by del X at the point X divided by delta, right? Now we can put this equal to constant C square, which is the diffusivity of the material, and we take the limiting case as delta X approaches to 0. So as delta X approaches to 0, what will happen? This del U by del T will become, sorry, del U by del T will become del U by del T in the limiting case. This is becoming the constant C square. And what is this? This is change of the partial derivative del U by del X with respect to X. So in the limiting case, this will change to del square U by del X square, right? So this is how we derive the equation of one-dimensional heat equation, right? So I hope you understood the modeling of one-dimensional heat equation. So thank you so much for listening to me. So if you like the video, do hit the like button and subscribe my channel to get the latest updated video. And always believe in yourself, you can definitely do it. Thank you. Have a nice day.